Okay, so this week, we're just going to do some work on looking at some applications of differentiation with exponential and log functions. So we're going to do some problems, and then you'll have to do some problems as well that have to do with curve sketching, finding optimization stuff like that. So let's start off just doing a little practice taking derivatives. So let's take a function. So these problems I'm doing come from the review exercises in your textbook. In chapter 8, this is page 560. And let's start off with number, let's do 37. So we have f of x equals 3 to the x minus 1. And it wants us to take the derivative of this. So we want to find f prime of x. And since this is a function that doesn't have the base e, we'll have to compensate for that. The first thing with the derivatives of exponential functions is to just repeat it. So 3 to the x minus 1. But then we compensate for the base not being e by multiplying by the natural log of that base, so natural log of 3. And then you take the derivative of the x minus 1. In that case, it's just 1, so we don't have to write that in. And we have our derivative. Similarly, let's do a log one. So let's do 43 is log base 5 of x. This is f of x. So if we do f prime of x, with log functions, the derivative is 1 over the input, so 1 over x. And then to compensate for this base not being e, we have to multiply on the bottom by the natural log of that base. So we get that. Then we take the derivative of the input. Derivative of x is just 1. So again, we don't multiply that. And we have our derivative. Then we have some logarithmic differentiation we can do. So 47, this is y equals square root 6x divided by x squared plus 1. So in logarithmic differentiation, the first thing we do is we take the log of both sides. And then we start simplifying that log expression. So we have the log of all of this. Well, this is 6x over x squared plus 1 raised to the 1/2. So I can bring the 1/2 down. And then I can separate the 6x and the x squared plus 1 because those are divided inside a log. That means they can be subtracted. So I'll really have 1/2 natural log 6x minus 1/2 natural log x squared plus 1. And that equals natural log y. At this stage, I can take the derivative of everything. To make this a little simpler, I'm just going to keep that 1/2 factored out. Okay. So now we take the derivative. We go 1 over y dy dx equals 1/2 times 1 over 6x times 6, because the chain rule there, minus 1 over x squared plus 1 times 2x, again chain rule. The 6's cancel. And we also want to just make this all one denominator, so this would be 1 over x and 1 over x squared plus 1, so this would be x squared plus 1 over x, well, minus x. And that way we can combine these. And so we get minus 2x squared, x squared, so minus x squared plus 1 over x times x squared plus 1. And we can multiply by y on both sides. And we get y, we need to substitute that back in. Put a 1/2 here. And then negative x squared plus 1 over x times x squared plus 1. And we get a differentiation. So that's just all the techniques of differentiation. We also want to be able to do some problems with this. So let's go on to finding some extrema points. So 55. y equals x cubed over 3 minus natural log of x. So first step to do when you're trying to find extrema and inflection points is you take the derivative. So we'll start off with the first derivative. Well, x cubed over 3, that's going to be, use the power rule on it, bring the 3 down, that cancels out with this 3, I get x squared. And then natural log of x becomes 1 over x. And we set this equal to 0 to find the critical points. Okay, so now I have the equation I need that is equal to 0. And now I'm going to actually solve this, right? I need to know where x equals 0. So we're going to make a common denominator. And so now I know that this is 0 when the numerator equals 0. And it's also a critical point when the denominator equals 0 because this is where it's undefined. Well, this one I can solve as x cubed equals 1, so x is 1, and x is 0. So those are my two critical values. So using my critical values, I can do a first derivative test on this because this is relative extrema. So with the first derivative test, I start off with making a number line with my two critical points on there, 0 and 1, label that x. Look at what f prime is doing and what f is doing. Actually, not f, because we haven't defined f anywhere in here. It's dy, dx, and y. Okay. So now we think about, well, what is the sign of the derivative, x squared minus 1 over x, when x is less than 0? So if I put in a negative number in here, well, the squared, I will just make it positive. And then I'd have 1 divided by a negative number. So that would be negative, but then it's minus, so it'll be positive. So I really have a positive number plus another positive number. This would be positive. So then y would be increasing there. Between 0 and 1, so now I think about, like, what if I put in 0.5? Well, if I just plug in 0.5, I can check that. I can do 0.5 squared minus 1 over 0.5. And that gives me a negative number. So that would be decreasing. Then I check something bigger than 1, so maybe 2. I can go 2 squared minus 1 over 2. And that gives me a positive number, which means it's increasing again. And so now looking at this, it increases then decreases. So this would be a maximum. And then decreases, it increases. This would be a minimum. So this is my work. It's not the final answer, right? This is just for me to organize my thoughts on this. But now I've got to actually conclude something. So looking at this, I can say that y has a relative maximum when x is 0. Well, let's also figure out what y is. Right, so at 0 comma, well, if I put in 0 in here, 0 cubed over 3 is 0, and the natural log of 0, well, what is the natural log of 0? That doesn't exist, right? It's undefined. So this doesn't actually work out, not in the domain. So we don't have that. The next thing we go is y has a relative minimum at 1 comma, well, here I can calculate this. 1 cubed over 3 is 1/3. And then I find a natural log of 1, which is 0. So it's 1/3 minus 0 is 1/3. Because y changes, dy dx changes from negative to positive. And then you also want to just put this in here that, make a note, x equals 0 is not in the domain of y. So we want to explain, right? Like we found x equals 0 as a critical number. We want to explain why we're not considering it. In this case, it's not in the domain of the original function. It made the derivative undefined, but it also makes the original function undefined. I really should have checked that earlier and not like only when I got here. What you should do is right at the beginning, write the domain up here and check for what values are excluded, because then you could just exclude it here instead of excluding it all the way here. So your increasing and decreasing behavior can still change at places where it's undefined. It could be an asymptote, it could be a whole. That stuff can happen. It's not a maximum or a minimum because the function doesn't actually have a point over there. But it still could change behavior, increasing and decreasing behavior there. Let's do one more problem, but I want to find a good one. There is one more problem I can show you, but actually, that one I want you to try doing on your own without me giving it away. So we'll stop this video here because I've given you some examples of what this looks like. And I want you to do a different problem I'm going to give you. I want you to try it on your own. And then I'll give you a way to check your work on that.